Hello everyone and thank you for watching this. LLMs are extremely powerful, but they come with significant computational and memory challenges. One critical component in this puzzle is the KV cache. As these models grow larger, managing the KV cache effectively has become a key factor for improving performance and reducing costs. My name is Moshe Tuito, a CTO and founder in Pliops, and today I'll share insight into KV cache offloading, analysis, and practical considerations. So this session will cover, first, why KV cache offloading is increasingly relevant in LLM inferencing. Then I'll introduce a simple yet pretty accurate analysis for both prefill speedup and end-to-end gain. Along the way, I'll share some very interesting insights that emerge from this analysis. Finally, we'll discuss the implications for storage systems. Okay. So the main use case for KV cache offloading is when the prompt of a query includes the previous prompt and its answer as a prefix. The simplest example of this is just a chat application. Let me walk you through how this works. So when a user sends an initial query, Q1, you see it here, the inference process consists of two distinct phases. The first is the prefill stage, where the input prompt is processed, and internal states, known as the KV cache or retention states, are generated. These states basically represent the model's memory of the processed tokens. Then the process moves to the decode stage, where output tokens are generated, and the KV cache is updated incrementally as each token is processed. For example, if we're going back to this example, when the user sends Q1, the model calculates the KV cache, generates an answer A1 here, and completes an interaction. However, due to the limited capacity of HBM or any fast memory, the KV cache is typically discarded after this interaction because it's just limited and there are other interactions that are going on in between. So now here's the challenge. When the user sends a second query, Q2, the chat application prepends Q1 and A1 to it. This means that the model has to recompute the KV cache for Q1 and A1 from scratch, even though it has already done that in the past. This recomputation happens every time a new query is sent, which leads to inefficiencies that compound as the session grows. So that's the problem. KV cache offloading addresses this inefficiency. Instead of discarding the KV cache, we simply store it on a large capacity storage, preferably SSD-based storage. This second query, Q2, when it comes, we just retrieve the KV cache for KV1 and A1 and avoiding the need to recompute it. The newly generated KV cache for Q2 and of course its answer A2 is then added to the storage, ensuring by that this efficiency is maintained throughout the session. So that's basically the crux of KV cache offloading. Okay, so now let's go on with the prefill speedup analysis. Okay, so before we analyze the prefill speedup, let's define the key variables that we'll be working with. This will help us to quantify the impact of KV cache offloading. So first we start with NIN. NIN, a number of input tokens. It represents simply the number of input tokens in the prompt. R here is the retrieval time for a single token's KV cache from storage. It's simply computed as the size of the KV cache per token divided by the I/O bandwidth. Next, T represents the compute time per token. This depends on both the model size here and the input length. This part, the second part, is due to attention calculations, and it scales roughly with the square root of the model size. This is an approximation. The denominator accounts for both model size and attention operations, while the denominator represents the available compute in teraflops. To measure the speedup from offloading, we define the effective token acceleration as E, which is T over R, This tells us how much faster or slower we can process tokens when leveraging KB cache retrieval instead of recomputation. Finally, alpha here represents the fraction of the KB cache that is successfully stored and retrievable. So now that we've defined the key parameters, let's analyze the prefill time and compare the vanilla system to a KB cache offloaded system. First, in vanilla system, the prefill time, or time to first token, which is similar, TTFT, it's just straightforward. It's simply the number of input tokens in multiplied by the compute time per token t, which also depends on in, but let's ignore this for the moment. Now for the KB cache offloading system, we have three parts that need to be done. First, we need to retrieve existing part of the KB cache. Second, we need to compute the new part of the KB cache, the Q2 from our example before, for example. And third, this new KB cache that was generated, we need to write it to the storage so this process can continue again and again. So we have both three components. Now, if you can overlap I/O and compute, the read and write I/O on the compute, then we can achieve better efficiency. And we're going to focus on this case here in this analysis. And I'll show later justification for that. So in that case, the time to first token of the KB offloaded system is just the maximum between the three components. The first one is the retrieving time, which happens to fraction alpha of the tokens, and it is done at a speed of t over e. Second, the write time of the new part, which happens to 1 minus alpha of the input tokens and speed of w per token. And third, the compute, which also happens to 1 minus alpha times n, but this time with compute time t. The maximum of all of those, or put differently, the slowest component determines the time to first token. And now, in the original equation, there are three potential bottlenecks: retrieve time, write time, and compute time. But can we eliminate one of those? Then, if you look on those two expressions, you see that to ensure that write I/O never becomes the bottleneck, we impose a simple requirement: W need to be at least as large as T. This means that the time to write a single token's KB cache must be no greater than the time it takes to compute the token. So, and if this condition holds, then the write term, 1 minus alpha times n in W, is always smaller or equal to the compute term, meaning it no longer influences the max function. So we can just omit it. So the first and most important takeaway from this equation is simple. Write performance only needs to match compute performance, nothing more. That's it. That's everything we require from write performance. Now, let's look on our new equation after applying W at least smaller or equal to T. The write term disappears completely. With the write bottleneck eliminated, what truly matters now is how efficiently we can retrieve the KB cache. This is where real speedup comes from. So now that we've seen how prefill time depends on read performance, let's refine our understanding further by introducing a key threshold, alpha star, defined here. Alpha star represents the fraction of KB cache retrieval at which the system transitions from being compute bound to I/O bound. So this is some sort of critical fraction of KB cache. So let's analyze both cases. The first case is the compute bound regime. Happens when alpha, the actual hit ratio, is smaller than alpha star. In that case, the system is compute bound, so the compute part is the dominant one. And in this case, the speedup is just 1 over 1 minus alpha. You see that the speedup for the prefill does not depend on the I/O speed at all. This means that even if you use faster memory, faster storage like HBM or DRAM, It won't improve performance. So sometimes people ask, what about DRAM? What about other stuff? In this regime, I don't care. The second case is where the hit ratio is high, alpha is higher than alpha star. And in that case, the prefill time is IO bound. And the gain in this case is E over alpha. And here, the prefill time is dictated indeed by how fast we can retrieve KV cache. The faster we retrieve, the higher the speedup. In this regime, storage speedup plays a critical role indeed. Now, if we look on this game, we can do a nice trick. Instead of retrieving all the stored KV cache from storage, in this case alpha, which is larger than alpha star, it's better to retrieve only alpha star from it. Why? Because this will enable us to maximally utilize both compute and IO resources. And in that case, we're going to get a gain of E plus 1. And why it's very interesting? Because if you do that, which of course depends on the capability to parallelize IO and compute, if you do that, then regardless of which regime we're in, the good news is that we always have any speedup as long as E larger than 0. So even with a low performance storage, we can still get some speedup. Of course, the faster the storage, the higher the speedup, but it's never lower than 1. So in the worst case, you're just as good as a system with no KV cache offloading. And this is, I believe, a very interesting insight. So far, we've discussed the theoretical performance benefits of KV cache offloading and the conditions for maximizing speedup. Now let's see how we in Pliops implemented this. So to achieve maximum parallelism between IO and compute, we need each layer to do 3 things in parallel. First, to read the KV cache of the next layer, write the newly generated KV cache of the previous layer, and third, compute the current layer's operation. Using conventional CPU-centric I/O introduces excessive CPU-GPU synchronization at every layer, increasing overhead and reducing efficiencies. Instead of Pliops, we built on NVIDIA's GPU-initiated I/O framework, where the GPU itself issues KV IOs to Pliops shared key-value storage, asynchronously without CPU involvement. This enables full I/O compute overlap at the 0 CPU overhead. Here you can see a real insight output from a real run, demonstrating how retrieval, you see it here in green, writes in orange, and compute in blue are all executed in parallel with minimal I/O overhead. Here, this case is for H100. The model that we used is Llama 3 70B. We used here 14K tokens, base size 4, and you can see here the actual results. The overhead, there's still some overhead here, about 10%, because when I'm issuing those I/O kernels, the GPU is idle. However, in our next release, we're going to put it on different stream, totally making this totally negligible. So now that we've covered the theoretical analysis, let's look at a real-world measurement of an IO-bound case and see how it performs compared to what we've discussed so far. This test was run on an A100 GPU with Llama 2 13B model, and here's what we observed. We used here alpha of 88%. The size of a single token KV cache is about 800 KB. This GPU has PCIe Gen 4, so the IO speed that we achieved was about 20 GB per second, which brings us to R of 41 microsecond, retrieval time of 41 microsecond. We measured compute time of 110 microsecond, which results in acceleration factor E of 2.7. Alpha star is, if you do E over 1 plus E, is 0.723, which means that alpha larger than alpha star, so puts us in the IO bound regime. So you see here that in this graph, the x-axis is the sequence length, starting from about 100 to 4K. I'm hiding this 4K here. The y-axis is the time to first token, the TTFT that was achieved. Here in the white line is the vanilla system. The blue line is the KB cache offloading system. You see that TTFT is much smaller. And you see that we got an acceleration speedup of x of 3x. That's what was achieved. What does it mean? Typically, those systems have some SLA, time to first token SLA. Typical number is 400 milliseconds. You see that vanilla system violates the SLA at relatively short front side. While if you do KB cache offloading, you can extend it much further. The third thing that you can see, this validates that indeed we are IO bound, this yellow dashed line. You see that it is well below the TTFT, the actual prefill time. And it represents the compute time of the entire prefill operation. So indeed, you see the compute is not a bottleneck, the IO is bottleneck. If we could achieve higher IO rate, the gain would be higher, as expected. We just saw an IO bound case where prefill speed was limited by the KB cache retrieval speed. Now let's examine a different scenario, one where the system is compute bound rather than IO bound. This test was run on an H100 GPU with batch size 4. We used, in this case, Llama 3 70B model, a larger model, but it comes with GQA, which is some sort of KB cache reduction or compression technique, which reduces KB cache size. So alpha is still the same. You see that even though it's much larger model, the KB cache of a single token is much smaller. It's about 300 KB. This is a Gen 5 PCIe, this GPU, which allows us to double the IO speed from 20 to 41 gigabytes per second, which means that retrieval time is as low as 8 microseconds of a single token, and compute time, because it's a larger model, it's 170 microseconds. This brings us a huge token acceleration factor of 20, which translates into alpha star of 0.95, alpha smaller than alpha star, so we are compute bound in this case. So what we expect from our previous analysis, we expect of a speed up of 1 over 1 minus alpha, which is 8.33. However, you see here that the actual gain is only about 7x. Why? Because if you remember, there was still some inefficiency in what you do. If you remember the insight chart. So this inefficiency makes IO parallelism not perfect, which reduced a little bit our gain. But still, gain is significant, very significant as compared to vanilla. And the final slide for this section is a presentation of the analysis of impact of IO compute parallelism that we discussed about it so much. So here in the x-axis is the cache hit ratio, the alpha. The y-axis is the prefill speed up, the gain, in relative numbers. And this shows how much faster prefill becomes compared to vanilla system without KB cache offloading. Higher values indicate greater acceleration. Let's start with the orange curve, which is without IO parallelism. This represents a system where IO and compute are executed sequentially. Retrieval happens first, followed by compute. While there is still speed up, it grows gradually and remains below 2. Now, the blue curve with parallelism, you see that retrieval, this allows us to parallelize IO and compute, and the significant improved speed up, especially as the cache hit ratio increases. So you see here very significant 2x gain compared to a system with no IO compute parallelism. Up to this point, we focused on the prefill stage, showing how KV cache offloading accelerates token processing. But as we remember, prefill is only one half of the story. In real-world inference, the decode stage, where the model generates output tokens one by one, it is just as critical, if not even more important. If you speed up prefill, but the decode remains slow, then the overall gain is limited. To fully understand the impact of KV cache offloading, we need to analyze its effect on both prefill and decode, particularly in continuous batching scenario, which is the most popular one. Ultimately, what matters is end-to-end efficiency, how much improvement we can achieve when processing queries continuously in continuous batching. Now let's dive into how KV cache offloading influences this end-to-end gain. In real-world deployments, inference workloads don't consist of a single request at a time. There are multiple concurrent requests, and the system must handle both prefill and decode stages. So let's go over the new variable that we need for this part of the analysis. First, B, the batch size, represents how many queries are being processed simultaneously in the system. Nout is the average number of output tokens. And the interesting thing that we base our analysis on is the number of concurrent prefills. And it turns out that it is approximately distributed, follows a binomial distribution. Why? Because you can think of the timeline as composed of consecutive time slots. In each time slot, you have B requests, some of them in prefill and some of them in decode. What's the probability that a single request is going to be in prefill? It's approximately 1 over Nout, because each Nout tokens there is a new prefill. So this just approximately follows binomial distribution. Now let's evaluate the expected TTFT as a function of the batch size B. You see it here. So the value, if you do there, it's very simple arithmetic. It's the time to first token of the first of a single request, while the second term here captures the contributions from additional simultaneous prefills. Effectively, this means that as batch size increases, prefill time grows, but at a slower rate due to the overlapping operations. You see here that this is the interference from a neighboring B-1 request, each of which is doing prefill at probability 1 over Nout. So that's the term that we get. Now let's go to the time per output token, or TPOT, and let's analyze the expected value of that as a function of B. So here again, it's the TPOT of single request plus B-1 times two factors, two terms. The first one is an inevitable one. It's the time that it takes to transfer a single prompt KV cache from the HBM to compute engines. And this is inevitable. When you increase batch size, you suffer from this degradation in time per output token. But this is the interesting part. This is the interference of concurrent prefills on the average TPOT. And we can reduce this one part significantly with our KV cache offloading. And that's exactly the mechanism through which prefill speedup or prefill gain translates into an end-to-end gain. Again, let's verify that our analysis match with reality. So here you see a plot for Llama 70B on H100. X-axis is the decode batch size, number of clients, starting from about 12 to 72. And the y-axis is the TPOT time, the time per output token time. And the purple line here is the TPOT where there are no concurrent prefill operations. This one captures the inevitable term that I mentioned before. You see that still, even if there are no prefill at all, still teapot increases linearly with batch size, but at a relatively low rate. Now look, on the other hand, on this, let's call it blue line. This is the average teapot. And you see that the slope here is much higher than here. And here we capture the effect of concurrent prefills on the teapot. That's the gap between the two, is the effect of concurrent prefills on the teapot. Let's now focus on what it means in practice. The key question that we want to answer is, how does prefill speedup translate into overall throughput gain, right? So let's again, with this equation of the expected teapot, it's a little bit simplified here. And let us denote this first term, the contribution of the prefill by delta P, and the contribution of the KV cache increase by delta H. Now, every system must meet a defined teapot SLO. For example, a popular number is 40 milliseconds per generated token. In order to maximize throughput and efficiency of the entire system, both the vanilla system and the KV cache offloading system must push their batch size as high as possible, right to the point where they almost violate the SLO. The batch size value that it achieves is captured by this equation. Now, the key difference is that in a KV cache offloading system, the rate at which the teapot increases with batch size is smaller compared to the vanilla system. Why? Due to the delta P term, which is in the KV cache offloaded case is smaller by a factor of X. This means that the offloaded system reaches the SLO at a much larger batch size. And since throughput scales with the batch size, the overall TPS, or tokens per second, the overall tokens per second gain is approximately equal to the ratio of the batch sizes, which is captured by this equation. And this term is upper bounded by, in the case that where x approaches infinity, which is just this very simple term equation, 1 plus delta P over delta H. Now that we've established how KV cache offloading increases batch size and improves throughput, let's take a step back and understand what fundamentally dictates the end-to-end gain. The key insight here is that the maximal TPS improvement is bounded by this term, 1 plus delta P over delta H. This means that even with infinite prefill speedup, the overall system gain is determined by two key factors, the key terms. Delta P, which represents the prefill impact on TPS, and delta H, which accounts for the memory bandwidth cost. Those terms are not arbitrary. They are dictated by the GPU, the model architecture, and the application workload. So to fully understand what drives end-to-end gain, we need to break down these contribution factors in more details. So first, let's break down TTFT of 1 to this, plugging in the expression from previous section. There are two competing terms, the model compute time and the attention compute time. We can define two regimes according to that. One, when n-in is small, and in that case, the first term is the dominant. And on the other hand, where n-in is very large, and in that case, the other term is the dominant one. Similarly to this, we can break down delta H basically to directly expressed by n-in as this. And now let's break down what influences the ratio delta P over delta H. As I mentioned in the previous slide, there are two distinct regimes. One, the short prompt regime, which happens where approximately n-in, number of input tokens, are much smaller than 6 times the hidden dimension. And the second, the long prompt regime, where a number of input tokens is much larger than 6 times the hidden dimension. Now, in both cases, after we plug in all the parameters, we get those expression to to capture the behavior of the ratio delta P over delta H. And in both cases, we see that this ratio depends or scales according to three factors. One factor depends on the model parameters or model architecture. The second one depends on the GPU characteristics. And the third one depends on the application behavior. So I'll let you work on those for a moment. Now that we've broken down the two regimes, the short and long prompt, we can analyze what factors influence the end-to-end gain in each case. So let's start with the short prompt regime. Then, according to the expressions that we've seen in the previous slide, and what we like to see. We like first large models because the first term increases linearly with the hidden dimension. So larger models means larger gain. Second, we really benefit from any KV cache compression or reduction technique. For example, GQA, MQA, and the recently introduced MLA by DeepSeek. All of those, we benefit from them. Third thing that we like is high memory bandwidth to teraflop ratio. For example, let's take the H20 GPU. You see there that this ratio is much higher than H100, for example. So it's good for us. Our gain there is expected to be higher. And lastly, we would like a shorter response because for larger response, the gain is somewhat smaller. Now, if we look on the other regime of a long prompt regime, then there are a lot of similarities, but there are some additional considerations to take. First, according to the first term, there is low dependency on the model size because it scales as square root of the model size. However, we still benefit from KV cache compression techniques, and we like high memory bandwidth to teraflop ratio. Another difference in that regime, in the long prompt regime, is that in this case, we depend on the ratio between input and output rather than the output alone. So it means that larger input to output provides us a larger gain, even though the output itself is larger. If the input is even larger, then the overall gain is going to be higher. So that concludes the insights that we can get from what factors and benefits KV cache offloading. So to wrap up this section, let's look at real-world results from running a shared GPT workload on Llama 3 70B model, floating point 8, which, if you look on the details here, falls into the short prompt regime with an average input length of about 2,000 tokens. And we compare a vanilla setup using Tensor Parallelism 4, which is the best option for vanilla execution, with Pliops setups using TP2 with KV cache offloading. All the tests were done on H100 GPUs. So let's look on the plot here. X-axis is tokens per second per users. So basically the throughput that each user is experiencing. And the y-axis is the tokens per second per GPU, which reflects the overall system efficiency. So the higher the TPS per GPU means that we can generate higher tokens per second and sustain more users. So you can see here, let's look on the blue line for the vanilla system. We see that as efficiency increases, the user experience decreases drastically. You see it by the fact that it's over here. While in our system, Pliops system with KV cache offloading, we get much higher efficiency at the same user experience. So if we take, for example, the popular SLO of 25 tokens per second, we see that we get an end-to-end gain for this shared GPT workload, which is a public recording of ChatGPT conversations. We see that we get effective almost 3x speed up for overall end-to-end gain with the KV cache offloading. So by reducing prefill overhead and enabling more efficient batching, we significantly improve real-world throughput while staying within SLA. That's conclude this section, and we can move on to storage system considerations for KV cache offloading. Now that we've seen the performance impact of KV cache offloading, let's shift our focus to the storage system challenges and considerations required to make all of this work efficiently. So let's capture here just the overall problem statement, which should be clear at this point. So modern LLM inference workloads run on clusters of GPU servers handling multiple users and multiple models simultaneously. And each request involves computing a KV representation during the prefill phase that is used to generate responses and extended KV cache accordingly. Given this setup, our goal is to design a storage system that can store and retrieve pre-computed KV states efficiently, ensuring that we accelerate the prefill phase, especially for recurring requests. And as we remember, by improving the prefill stage, we also introduce an end-to-end gain. So that's just the problem statement. Now, here are the key requirements that we believe are important for any storage system that is designed for storing and retrieving KV cache. So first is data sharing. One key advantage is enabling cross-server data sharing. In many deployments, system schedulers dynamically assign requests to different servers. This means that a request might start on one server, but a follow-up request could be handled by another. Without shared storage, this may lead to either redundant computation or suboptimal load balancing. By allowing key value data to be retrieved and stored across servers, we eliminate this inefficiency, improving load balancing for all those multi-turn interactions. A second requirement is zero application friction. A KV cache offloading system should be seamless to integrate, meaning retrieval should be based only on content without requiring session or using association. This both simplifies application logic and enhances security by removing unnecessary state tracking. Third requirement is about performance. We talked about that in length during this talk. And last, but certainly not least, we want the system to be not just faster, but overall more efficient, factoring in not just the GPU saving, but also the cost and power of the required storage system. So overall gains should be translated into a lower TCO per token, tokens per dollar, something like that, and better power efficiency, which is expressed by tokens per watt, for example. In other words, acceleration should be cost-effective and scalable. Now that we understand the key requirement for KV cache offloading, let's evaluate different storage options that we all know and see which best meets our needs. So let's go through the options. First is local storage, either DRAM-based or SSD-based. It is clearly not suitable because it's tied to a single GPU server and cannot be accessed globally. It's violating the first requirement that we have of data sharing. Next, if you go to shared block storage, SAN storage, then it is indeed a shared storage. However, it lacks a shared consistent index across the GPUs. It's just a bunch of blocks. That's it. And of course, we need some consistent index in here. So a shared block system is just not a complete solution for us. Next, let's examine traditional file systems and object storage. To understand if it's a good fit, we need to understand a little bit the I/O pattern, I/O size, for example. If we look on the requirements, let's start with the requirement of content addressable storage. If we want to have an efficient content addressable storage, it means that we need to break the entire prompt and all the tokens into chunks, multiple chunks of much fewer tokens. For example, chunks of 16 tokens or something like that. Why? Because we effectively want to implement an efficient prefix tree that spans all the different requests in the system to eliminate redundancy, to be able to build it on the fly, etc. So the fact that we are using much smaller chunks means that instead of having huge files where object storage and traditional file system excels at, we have a lot of relatively small files. To add even more complexity to it, remember our requirement for I/O compute parallelism. This requirement means, if you remember, that we want the I/O to be done on a layer-by-layer basis. This requirement drives the I/O size even much smaller. The I/O size, not necessarily the file size, but the I/O size is much smaller, to be on the order of multiple k bytes, multiple 10Ks of bytes. You can put on top of that a tensor parallelism, where each key or value vector is spread and broken across multiple GPUs. Some network compression techniques. If we want the system to be efficient, then we don't want to add a lot of networking requirement to the system. Remember that we introduced a new networking tool on the system that was not exist before. Before, just simple prompt was in. Now we need to read all of those relatively heavy KV cache data. So in order to a little bit reduce this cost, we can use compression over the network to further reduce the network requirement. This results in overall all of those requirements means that the I/O pattern is behaving as small random IOs of variable size. It's also justified the NVIDIA Next storage requirement, for example, if you're familiar with them. And file systems and clearly object storage are just not a good fit for that. They're very good for very large accesses of hundreds of kbytes, megabytes, but in our case, we need to have variable size, random, small IOs. So this makes file systems and object storage to be not to be a good options. So what we believe are good options: a storage system that basically was built for such use cases. This is distributed key value storage. Why? First of all, it is shareable. It has a built-in consistent index, clearly that the essence of key value store. And it was designed to work relatively good for small random IOs. So that's a good option. However, if we want to take the efficiency requirement and make it even much better, we believe that what we should do is to take each node in this cluster, key storage cluster, and make it as fast as possible. Why? Because in this way we can reduce the overall footprint of the KV store significantly. So the cost and power can be driven down. We call this option accelerated distributed KV store, and that's the approach that we at Pliops are pursuing. We accelerate the storage by a dedicated hardware that can extract from a single node tens of millions of IOPS, tens of millions of get and put operations per second, which means that with a very small amount of storage node, of key value storage node, we can satisfy a very large amount of GPU servers with very small cost and small power and low power. So the conclusion here is that distributed high-performance key value store emerges as the best option for KV cache offloading. Up until now, I've been all about analysis and performance insights, but on this slide, I finally do some actual marketing for Pliops, so let's now talk about how Pliops XDP delivers the required efficiency that we discussed. So a KV cache offloading is going to be truly scalable. So Pliops XDP is the name of our product, provides a hardware-accelerated key-value engine built on a dedicated ASIC built or composed in a low-profile PCIe card. This product enables extreme performance, achieving 30 million read IOPS and 15 million read-write mixed IOPS per card, and we have multiple cards per system. With such high throughput and IOPS, we can significantly reduce the number of required servers, lowering data center footprint, power consumption, and operational costs. Beyond just high-speed storage, we also employ several data reduction techniques to further improve efficiency. For example, compression to reduce storage footprint and bandwidth, adaptive per-layer quantization to minimize KV cache while still maintaining accuracy, and token pruning to eliminate unnecessary tokens, reducing our traffic even further. All those techniques not just improve efficiency, but also lead to increased data size variability, and our system is excellent on such workloads, so we can sustain this load very naturally. So the bottom line is that by combining hardware-accelerated key-value processing with compression and quantization, we achieve end-to-end system efficiency, delivering high IOPS per dollar or watt and low networking overhead, making large-scale key-value cache offloading both practical and cost-effective. At the end of the day, KB cache offloading, as you remember, isn't just about making inference faster. It's about making it scalable, efficient, and cost-effective for real-world deployments. And with that, I really like to thank you all for your time. Thank you.